Hi, my dear friends, and nice to meet you again. And let's start lesson 19. In this lesson, we're going to talk again about stacks and queues, but this time we're going to implement them using the concept of linked lists that we have just introduced in the last two classes. In this presentation, we're going to talk about the stack as an abstract data type, an ADT, excuse me. And then we're going to talk about the implementation of stacks using linked lists. And then after that, we're going to redo all the operations we performed on stacks, but this time using this new way of implementation, which is basically the linked list rather than the static structure of the array. So stack operations, and let's start from the very beginning in here. Actually, we're going to talk about this topic in this lesson and in the coming lesson as well. Stack is an abstract data type. Remember when we talked about abstract data types and that it doesn't matter how they're physically implemented actually inside the computer. What matters to us as programmers or as users is actually how we talk to these structures and how we operate on these structures, no matter what the details of the implementation is inside it. So I look at it as a black box, transparent to me as a programmer, and I refer to it, I use it, and I perform functions on this structure without actually knowing or needing to know what's exactly inside this box. And that's what we call an ADT, an abstract data type. So we can use a stack calling key functions. Remember that we have used create to create a stack, basically, and then to perform the push operation to where I add an entry on top of the stack, or to pop something from the stack, and that's basically to retrieve the last recently inserted item from the stack. So basically, this is the conceptual view of the stack, to where I put on top of each other all my entries, and I'm always operating on the very last entry in my structure. Okay, so when I push, I always add the new entry as the last entry in the structure, in the stack, and when I pop from the stack, actually I service or I retrieve the data that's on top. You remember the structure, we're just repeating here just to refresh our memories about the concept. So we talked about create before. We talked about the push operation, pop operation. Of course, we implemented these using arrays a while ago, and now we're going to revisit all of these functions assuming the linked list implementation. Other functions that we have covered is stack top, to where I would like just to copy whatever I have in this entry to another entry outside without changing the position of the stack pointers, without changing the stack as a whole. All right? And another function is where we checked whether the stack is full or not. Okay? So that was, if you all remember, a kind of Boolean function to say a yes/no kind of thing, because I needed to do that before I can push a new entry to make sure that I don't have overflow. Or on the other side, to check if the stack is empty, as a matter of fact, before I can pop or retrieve anything from the stack. Okay? And I had to do that again to make sure that I don't have a sort of underflow. These are basically the kind of operations we talked about when we introduced the concept of stacks, and we have already implemented all of these functions, but at that time we assumed that we use the array structure as the basic structure for implementing the stacks. Well, basically, let's look at this model. We have seen a slightly different picture, but basically the same kind of concept in here. The kind of layered, hidden kind of layer in between the user and the actual hardware and what's physically implemented on the memory. Basically, my functions, my basic functions, this create, pop, push, empty, not empty, full, whatever, are actually sort of public and private functions kind of thing. And actually, these functions are they have some sort of an interface with the user. So for me as a programmer, I'm sitting outside here Okay, and when I want to call the function push or call the function pop, I have a sort of standard interface between me and these public functions or private functions. Actually, this interface, the one which I see, are actually what's so-called public functions. Of course, these public functions could call each other's. Remember, when I used to call the function push, for example, I had first to check whether the stack is full or not. So this function might call another function actually in the process. This function could be another public function or could be a private function, to where I don't, as a programmer, call that function, but rather other functions are using it. Okay? Where is the structure in this whole picture? Well, the structure is back behind here. Okay? It has a data path or a data flow that connects it with these public and private functions. I, as a programmer, as a user, I don't have direct access actually to the data structure. I don't care. I don't need to have a direct access. What I need to have is an access to these functions that serve and work on these structures. What does that mean? That means basically is that the implementation of this data structure is irrelevant to me. As a programmer, I don't care how this structure has been implemented, whether you put it in an array, on a linked list, in a binary tree, in a network, in any kind of thing. That's irrelevant to me as a programmer, as a user of these functions. Rather, these functions here are going to actually operate directly through this data flow, through this data path on these data structures. So when the data structure changes, maybe I would need to make some changes here on these private and public functions. However, my main program, which basically has an interface with these public and private functions to where I input my data and get my results out, all right, this is not going to change regardless of the structure I have in here. And this is a very important concept, and this is called a layered model, if you like, for building your software. So if the technology changes and people come up with new structures that are more efficient, faster, utilize memory better, they need less space and all of that, you can definitely use that structure and make the minor changes to these private and public functions. However, your program, as a user program, as an application, is not going to be affected with these changes, as it's going to keep working the way it is without any change. Excellent. Okay, that means I could have multiple implementations, as a matter of fact, of the same concept of the stack in this case. Well, an ADT can have several implementations. That's true. And that talks basically about the data structure, which is actually way hidden from me, and I don't talk to it directly, but rather I talk to the interface functions in between. So implementation may be different, but implementation details are hidden. And I don't need to know these details, as a matter of fact, as a programmer or as an application. So the interface functions, they stay the same. These interfaces are actually what connects me as an application to these private and public functions, basically. As long as this interface stays the same, then I don't care what happens inside that room. As long as I know how to get to the entrance and how to insert data through that entrance and retrieve data through that entrance, then I don't care what's cooking inside it. Okay? As long as the data goes in and out the way I like it to go in and out. So interface functions stay the same. Application programs will not see this difference, will not see any difference, and they're basically going to stay the same, as I said. Well, this is a big advantage when we actually develop our programs. That means if there is a better data structure, then why not changing our whole structure that contains the data to a better data structure that could basically serve better my application and could save time on the computer or save memory and so forth. And that's exactly the idea behind this whole thing. we would like to implement the stack using linked lists. Why is that? Is it just because we just learned linked lists and we would like to use them? Is that a reasonable reason to do it? I don't think so. Actually, we have realized that these linked lists are more dynamic and more flexible than arrays. How's that? Well, remember the limitation, the bound limitation of the arrays is that I had to assign ahead of time at the very beginning of my program when I write it, the maximum number of entries that I can have. Well, and that could cause the problem of overflow in the middle of my program, or the poor utilization if I realize that I'm not going to need that whole space in the memory. Well, that's a restriction on the arrays. And then the linked list, they don't have this limitation. Basically, anytime you would like to add a new entry, and only that time, you're going to allocate a space for it, and then you're going to add it to your list. If you don't want that space anymore, you can destroy it. You can delete it. So it's a much more flexible structure then, and a more dynamic structure than using arrays. And I believe this is a good reason why we would like to switch to linked list implementation rather than the static array implementation. Definitely, these data structures, the linked lists, are more efficient in using the memory rather than the arrays. And again, this is due to the static declaration at the very beginning of the size of the array. No need for contiguous space in memory, and this is a very important reason as well. Remember, to reserve location for a memory, I have to find enough space, contiguous space in the memory map, and that space is going to be all allocated for this array. So before I can reserve a space in the memory for the array, I have to find an enough block in size to allocate that memory. And in here, I'm going to have all the entries, as we said earlier, in rows, row after the other for the entire array. So the whole array starts here, and the next item comes one location after that, two locations, and so forth till I get to the very last location. I cannot have bits and pieces of the array here and there. It has to be contiguous. Well, this could be a problem. Why? Because simply the memory is being used by other applications, and you have pieces of memories here and there. Okay, and you want to accumulate 1,000 entries. Fine, I do have 1,000 rooms for them, but I don't have them as neighbors next to each other's. Well, I'm sorry, if we're talking about an array, then I cannot do that. It's either you you rent me 1,000 consecutive rooms, or I'm not playing the game. Well, that's a problem. In case of linked lists, well, if you have the 1,000 locations for the 1,000 entries, that's excellent. That's all I want. Okay? They don't have to be contiguous. They can be anywhere in the memory space. It depends upon the space that you have. So I just tell you, and I'm here, the program, and you are the operating system. Please, operating system, I need one extra room. Okay? Reserve that for me, and just tell me where the address of it so that I can point to it to be able to traverse, of course, the whole rooms. This room or that room doesn't have to be one after the other. They can be anywhere in the space. And this is one more reason why I would like to switch to linked lists rather than sticking with arrays. Of course, accessing the different nodes or the different rooms comprising the linked list, when we talk about this linked list implementation, is going to be a little bit more tedious and than accessing the array, of course. Because if we're talking about the array, then I know if I want to get to the 5th node, then it's at position 1, 2, 3, 4, 5 from the beginning of the array. I know where is that right away. And I can go directly to number 5 simply by specifying the index which we put between the square brackets. So I say I want to go to the ith element in the array. So simply if this is A, the pointer A, then this is just A plus I ahead of this pointer. and I can go there straightforward. And to do that, I don't have to pass through number 1, number 2, up to number I minus 1. However, as a limitation on the linked list, if I need to go to the ith room or to the ith node in the linked list, then I'm afraid we have to visit them sequentially. Why is that? Simply because I don't know where exactly the ith node is located. Okay? Its address, all right, is located in room I minus 1. However, to get to room minus 1, I need to get into room minus 2 so that I know the map which leads me, the road which leads me to room I minus 1 and so forth. So the basic restriction on linked lists is that the accessing is always sequential. However, with arrays, it can be random. And this is the only, if you would like, the only disadvantage for using linked lists as compared to arrays. Okay, let's now, given these reasons, and I believe they're satisfactory reasons, let's now implement stacks using linked lists. This is a view, a conceptual view of the stack. It's a container basically, and the items in here or the nodes in here are going to be stacked on top of each other like that. And always, whenever I have a new node coming, okay, I'm going to place it on top of the stack. And whenever I would like to retrieve anything from the stack, I'm going to be retrieving the first entry on top of the stack. So it is a last in, first out kind of structure. We remember that. So this is the conceptual view. However, if I implement that using linked lists, well, simply, I'm going to have two main definitions. One, to define the stack itself. Remember, I will draw this, this figure in a slightly different way. It's basically something like this, the one we have already used to in the past few classes. So it's something like this. Okay? And there are basically two structures defining this. One structure is what defines the head of the stack, and we use to actually have more than just the head pointer in there, which points to the first node, which is the top of the stack in here. We used to have another integer, which basically keeps track of the number of records or number of nodes that I have in the stack. So basically, that is this structure in here that we have, which has count and top, basically refer to the number of nodes that I already have in my list. And this top here is a pointer that points to a node, a linked list node. And these are actually consecutive nodes in my list. This is the top of the stack, okay? And it refers, this one refers to this thing, to this block. In here, I have my data. So the data goes here, basically. And in here, I have a link that points to the next node in the list. And again, this is another node. Okay, I have data in here, and I have a link that points to the next, and so forth, till I get to the very last one down here. Data and pointer, and at the very last, the pointer in the last node at the end of the stack is basically pointing to null, indicating that there's no more entries in the list. So it's pretty much the same, an exact linked list. We're talking about two basic structures here. One which defines the stack as a whole, or the linked list as a whole, and another structure actually defining each node in the stack. Okay, based on this, what are the basic operations that can be defined on stacks? Well, first of all, I need to create the stack. Well, to create a stack, I need to build or to create the structure defining the stack. Basically, the structure create, allocate in memory location for the structure, which talks about, which defines head as a pointer that points to nodes of this type, and integer that will count the number of entries I have in there. Of course, when I create this, I don't have any entries, so the count is going to contain 0 basically, and the head is going to be pointing to null. Means, okay, I have a pointer that's going to point to a list. However, I don't have anything in the list yet. All right, so the initialization is going to be to put a 0 in count and make head pointing, or top in this case. And we would like to call it top to keep the same notation that we used for stacks. Okay, so it points to null. Top points to null in that case. So at the beginning, I need to allocate space for this structure. And then after that, I put a 0 as count, nothing so far in my stack, and make this point to null. In these graphical illustrations, I'm going to use the cross in here to indicate that I'm pointing to null instead of this earth notation that we used in previous slides. So basically, what I'm doing in here, I'm just reserving a pointer that's going to point to this container. The container is empty now. What can I do after that? Well, I can definitely start pushing data to the stack and stack entries inside my stack. How to do that? Well, basically, it's like insert a node into a list. Where am I going to insert it? At the beginning, in the middle, at the last. These are the different scenarios that we have learned when we were talking about linked list. Well, no, this is a kind of restricted, if you remember, restricted linked list to where I would always add on top, right? So the insertions are going to be always at head, at top. And that's conceptually the meaning of a stack. So in that case, I don't have any entries so far. So this is the initial status that I have, okay? I had 0 in here and this one pointing to null. I have a new customer. All right, I'm going to add it to the container. This customer, the data in there called green. Okay, fine. Then instead of making this point to null, I'm going to make it point to this new node. So I'm going to create a node, place the data inside it, green. Okay, make it point to null. That's the way we create a node, a list node. And then hook it up to the list. Hooking it up means make this point to this node. So instead of making this pointing to null as it was here, it's now gonna point to this node. Okay, and inside it I have green, and in here it's pointing to null. That's like having conceptually something like this. My container contains one entry. Okay. So basically, that's how my list is going to be. It contains just one node, and the structure here is just defining this pointer pointing to the beginning of the list, and with a count of 1 indicating that I have one node in the list. All right. Another push. Another customer comes in, and this customer is called blue. Again, I'm going to create the node. Right? Fill it with the proper data. The data in here is blue. Okay? Make its pointer point to null. That's when I create it. All right. I'm going to insert it to the queue. Where do I insert it? On top. Okay. So I'm going to make the first step. Remember the insertion at the top. This is the new node. I create this one. Okay? I filled in the data. The data is blue. When I created it, I made it point to null. All right, now I want to insert it to my existing stack. How do I insert it? You remember when we add a new node to the top of the list. Then I'm going to make it point to here, to wherever head is pointing instead of pointing to null. That's step number 1. Okay, then after that, I can safely move this pointer, which is top or head, and point here. That way, I have the list like that. So all pushes are like insertions to the top of stack. And that's what we did in here. Okay? I basically created this node, filled it with the data. Okay? And then when it was created, it was pointing to null. Instead of pointing to null, I'm taking it and making it point to this node, green, the one which I already had in the list. Okay? And then instead of having this pointer top pointing to green as it was before, I can now change it to point here safely without losing any data, because this data is already pointed by this arrow in here. I'm not showing all the steps because it's very straightforward and simple, and you know it. So at the end of this, I'm going to have a count of 2 now, because I have 2 nodes, and this is the conceptual view of the status of my stack. Let's say I would like to pop the entry on top of stack. Okay? Pop always, it's like delete a node. And again, deletion could be from the beginning, middle, and end. Well, if we're talking about a restricted linked list, then we're always going to be removing the entry on top of the stack. All right, here is my list. And here is top, pointing to the beginning of it. All right, and I would like to pop from the stack. That means I would like to take this out of the queue. Well, simply what I'm going to do, I'm going to make a pointer point to it, and then I'm going to take this pointer to point to the next, and then I have it pointed by this one. I could delete it after that, or I could process it the way I like. What matters is that it's no more part of my list. So basically, what I do when I pop from the stack, that's what I have before. That's the situation. I have 2 nodes, okay, and the count was 2. And then on the next slide, what I'm going to have, this blue has been removed from the stack, doing these steps basically, and then I'm going to end up with only 1 entry, count says 1, and now top is pointing to green, and I only have 1 entry in here left. The item that I removed is the last entry that I pushed actually, which is the blue. All right, so I'm serving always the entry on top of stack. What if I would like to destroy a stack? Destroy a stack means clear the stack. Remove all entries from the stack. All right? How to do that? Well, the stack I have in hand contains only 1 node. So basically, I like to destroy it. All right? So I will make top just point to null, make this equals to 0, and free all the space in here. Okay? So basically, it's the same steps like going, even if this list was very long, then I'm going to go from the very end, delete the last one, go back, delete, go back, delete, go back, delete. So I'm going to keep deleting one after the other till I get to the very beginning, to the pointer, and make it point to null. Simply, I can make always this point to null, and the whole thing flies in the air like balloons. All right? However, the space is still reserved in the memory. Remember that? To physically destroy all of these entries and make the space available for other applications, I have to free that space. And that's why I have to go to the very end, delete that one, delete the one after, and so forth till I'm done. I cannot do it from here right away because the space for these is going to stay reserved in the memory and nobody else or no other application can use it. So basically, after I'm through with deleting all entries, the stack would look like this. No entries in my stack, top is pointing to null, and my container is simply empty, doesn't contain anything. Okay? So I'm going to keep the structure, the pointer that points to the stack. However, the stack is just empty. That's what we mean by destroy stack. Okay. Let's now get to the implementation and look at the key structures that I have. Basically, I said we have 2 main structures. One to define the whole list, the stack, basically top and count. That's the structure. And it's just a pointer to the whole list of nodes and a number counting these nodes. And the second structure is basically to define each node. All right? So these are the 2 structures. This defines the node, and this basically defines the head of the structure or the top of the structure, which is basically a pointer, a pointer to the node and a count, counting the number of nodes contained in my structure. So basically, the stack itself is defined like this. I will have a count, basically of type integer. This is a pseudocode. We're going to write the C code in a second. And top of type pointer to a node. And that's basically the definition of the stack. Only this, top and count. The node itself, however, contains inside it the data. So I'm going to have a bunch of variables, basically of certain predetermined data types, floats, integers, text, names, whatever. Okay? And what's important, this is all just regular data, regular variables. However, what's important is that I have a link always that points to another node similar to this one, this pointer. Remember that. And we have talked about this thoroughly when we were talking about linked lists before. Okay, let's write these structures in C. Basically, this is the stack node definition. It's a structure called stack node. It has some predefined data type called stack entry, which defines all the variables inside it. And the name of the variable is entry. So that's basically the data I'm having inside each node. And basically a pointer called next that points to a node of the same type. And this will contain the address of the next node whenever I have a next node. Otherwise, it's going to be just null. Okay? And we're just giving it the name stack node. On the other hand, the definition for the stack itself is basically another structure in this case, and we're calling it stack. It contains two variables, an integer variable called count, which basically is going to give me always the number of nodes that I have in the list, and the variable top, we used to call it head. In this case, we're calling it top to refer to stacks. Okay, and it's basically a pointer to a stack node on the previous slide. So it points to a node like this. All right, and the name of this structure is stack. Okay, create stack. Create stack is a simple function which will reserve in the memory just a location for the structure defining the stack itself. No nodes in there. Okay, just allocate in the memory a space for this, for top and count, this structure called stack. Okay, and make it point to null. Put count equal to 0 if everything was successful. Okay, so the name of the function is create stack. It's going to return a pointer to that stack, and this pointer is actually what I'm going to call top or head later on, or my stack, whatever. So it doesn't take any arguments. Basically, we used to give, when we created this using the array implementation, a maximum number of elements. Remember that? Well, I don't need that anymore. In there, I had to allocate a specific size for the array as a maximum size. Well, I don't have to worry about this anymore in here. And that's the fantastic thing about linked lists. And actually, my stack in here can grow as far as the memory can accommodate entries. As long as there is space in the memory to allocate for new nodes, then I don't have any problem. I can grow my stack, or my stack can grow the way it likes to grow. So that's why I'm not passing any parameters basically in here. Preconditions, none. Post conditions. The stack will be created and initialized to be empty. That means count equals to 0 and top points to null. Okay, let's look at the C code. Create stack. Okay, the local variable is called stack. And basically, I'm going to allocate the size of stack structure. And if it is successful, if it doesn't equal to null, that means make top point to null and make count equal 0. And then return stack. Very simple, very straightforward. No mentioning for any maximum size in here, again. let's see how we're going to implement the push operation. And I think today we're going to finish with this, and we'll continue on the other operations next time. Let's see. The push, I'm going to insert a node to the top. Okay? Always to the top. And same as inserting a new element into a list before the first. And we have done this code before. We're just revisiting it very quickly. Okay, so the steps: create the new node, fill it with whatever data you would like to fill, and make a pointer point to it, new node. Okay, and make this point to null basically. And then here's your existing list. It already has like 2 entries inside it. Well, okay, just make this link point to the first entry here, if you all remember. Then you can make this pointer to go here. And then you're done. True? And that's the only insertion we're going to do, not anywhere else. Okay? So basically that's what we're going to do. This is step number 1, and then this is step number 2. This is not 0 here. This is top. The function. Prototype. It's going to return a value of integer. We're going to see what this integer is. But basically, it takes stack entry, the item that you need to insert it, to this stack. Okay, what we're going to do. The preconditions, the only condition is that this stack already exists. As a result, the argument item is going to be stored on top of the stack, and it will return 1 on successful. That's why I'm having an integer here. I will return 1 upon successful, otherwise I'm gonna return a 0 or anything else. Okay, let's see the code. Basically, I'm defining a pointer to the new node, calling it new pointer. That points to a node. And then I'm allocating memory using the malloc function to allocate the size of a stack node. Okay? And cast it to be of this type, of course. If this is successful, okay, then I'm going to fill it with the data. If it equals to null, that means I could not allocate memory. The memory is full. There is no space in there. If that's the case, return 0, and the 0 in here means unsuccessful return. However, if it was successful, then basically make the new entry. Here's the new entry. This is the new node. Make this arrow next point to the first one. This is step number 1. True. And then make top point to this. This is step number 2. Right? And that's what we're doing in here. New pointer. Arrow entry equals to item. We're filling it with the data. And then new entry or new pointer. Arrow next equals to s arrow top. Okay? This is step number 1. And then s arrow top goes to new pointer. True? And we have seen these 2 lines before. Before I just go back, I need to make sure to increment my counter in here, as I have 1 extra node in my list. And then this is a successful return, and that's why I'm returning 1. Okay? It's very simple, very straightforward, similar to what we have seen before. I'm going to stop in here today. If you would like to see this, the material I have presented, you can definitely go to the internet, to the UNINETTUNO website, click on the MidNetU project, and you're going to find lots of interesting stuff. Thank you very much for watching. I'll see you next time.